Chapter 12, Section 2 is on differentiation and integration of vector-valued functions. Theorem 12.1 is the differentiation of vector-valued functions. If r of t is your vector-valued function with components I and j, or f of t and g of t are the functions of t, then r prime of t is found by simply taking the derivative of each of those differentiable functions for each component. If for the plane, and then adding that the k vector, finding the derivative of a vector valued function in space is found the same way, taking the derivative of each of the components. In this example, we are finding the differentiation of vector valued functions for the vector valued function given by r of t, which is equal to ti plus t squared plus 2j. Find r prime of t, then sketch the plane curve represented by r of t and the graphs of r of 1 and r prime of 1. For the solution, we're going to differentiate on a component by component basis to obtain r prime of t. Now the derivative of t is 1 and the derivative of t squared plus 2 is 2t. So we get r prime of t equals I plus 2tj. From the position vector r of t, you can write the parametric equations x equals t and y equals t squared plus 2. This gives you a way that you could sketch the original vector valued function. You can also do this using parametric mode on your calculator to sketch the function and pay particular attention to when t is equal to 1. When you use this method of eliminating the parameter, you get the equation y is equal to x squared plus 2, and that's going to be the same graph that's resulted if you're using parametric mode. When t equals 1, plug in 1 into the original vector valued function for t, and you get I plus 3j. Plug 1 into the r prime of t function to get I plus 2j. We're going to graph the path and the vectors r of 1 and the vector r prime of 1. Now the dark line with the arrow indicates, or the curve with the arrow indicates the path, and at the point when t equals 1, you can sketch the position vector, or r of 1 vector, from the origin, and that terminal point of that vector is a point on the path. For r prime of 1, you sketch it with the initial point on the path, and using the components 1, 2, you see that dark black vector line is your r prime of 1 vector. Notice that the r prime of 1 vector is tangent to the path at that point, where the position vector r of 1 is a vector drawn from the origin with the terminal point on the path. Now I have a few more examples that I'd like you to try on your own, where we're going to be finding the derivative. If r of t is equal to 1 over ti minus 3j, find r prime of t. You can pause the video now and then restart the video to check your work. When you're done with that one, try this one, r of t, which is equal to t cosine ti minus e to the negative t squared j. Again, you can try this one on your own, find the derivative of each of the components, and then restart the video to check your answers. To find r prime of t, if we're given r of t equals 1 over ti minus 3j, we are going to find r prime of t by taking the derivative of each of the components. Now remember that if you have 1 over t, that is the same thing as t to the negative 1 power. And when you use the power rule to find the derivative of t to the negative 1 power, you're going to write this as a negative 1 out in front, t to the subtract 1 from the power to get the negative 2 power. That's your I. And then the derivative of minus 3 is 0. So you can write this as 0j. And when you simplify r prime of t, you get negative 1 over t squared I as your derivative r prime of t vector valued function. Okay, find the derivative of this vector valued function r of t equals t cosine ti minus e to the negative t squared j. We find the derivative of each of the components, r prime of t. When we're taking the derivative of the first component, t cosine t, we need to use the product rule. This using the product rule, the derivative of t cosine t is the first, which is t, times the derivative of the second. Derivative cosine t is negative sine t. First times the derivative of the second plus the second, which is cosine t, times the derivative of the first. And the derivative of t is 1. That's all of that. That's your I vector. And then minus the derivative of e to the negative t squared. The derivative of e to the u is e to the u times the derivative of u. So that it's going to be minus e to the negative t squared times the derivative of negative t squared, which is negative 2t. And that's your j component. Let's simplify that to get our negative t sine t plus cosine t, all of that is your I, plus 2t e to the negative t squared j. So that's going to be our r prime of t vector valued function. Here are some examples of integration of vector valued functions, but before we get to these, let's talk about what it means to be smooth on an open interval. The parametrization of the curve represented by the vector valued function r of t, which is equal to f of t I plus g of t j plus h of t k, is smooth on an open interval I if f prime, g prime, and h prime are continuous on that interval, and r prime of t does not equal 0 for any value of t in the interval. For this example, we want to find the intervals on which the epicycloid c, given by r of t equals 5 cosine t minus cosine 5t I plus 5 sine t minus sine 5t j, where t is between 0 and 2 pi, is smooth. So we want to find the intervals where this vector valued function is smooth. Going back to the previous slide, we say it's smooth if all those derivatives are continuous and if r prime of t does not equal 0. So we know that the cosine and sine functions are smooth, but so we want to find out where r prime of t equals 0. Wherever it's equal to 0, there is a possibility that there is something about the path that is not smooth. So to find the solution, we want to take the derivative r prime of t. Taking the derivative of your components of your vector valued function, we get this equation for r prime of t. Now the only values of t were for which the first and the second components are equal to 0 at the same time are where t equals 0, t equals pi over 2, pi, 3 pi over 2, and 2 pi. And you can find out where there's 0. You can set the whole thing equal to 0. If sine is 0, we know that the first component is 0, and so on. Now, because those pi over 2, pi, 3 pi over 2, and 2 pi are the points where r prime are the values of time where r prime is equal to 0, we say that it's smooth everywhere in between those intervals. And this is a graph of the epicycloid. We say it's not smooth at the points where it intersects the axes. Now this slide shows different properties of the derivative. You can review these properties. The first one is the derivative of a vector valued function that's multiplied by a constant. That's the constant rule. We have the addition rule. The this is the product rule is number 3. We have dot product, cross product, chain rule, and the dot product. For this example, we're going to use the properties of the derivative for the vector valued functions that are given by r of t equals 1 over ti minus j plus natural log of tk, and u of t equals t squared I minus 2tj plus k. For part A, we want to find the derivative of r of t dot u of t. You can do this a couple of ways. You can find the dot product of r and u, and then take the derivative of the result. For this one, we can find the cross product of u with u prime, and then take the derivative of the results. Or we can use one of the properties that are listed in the previous slide. Okay, so by using this property, we find r prime and u prime, and the dot product of the derivative of the dot product of r and u is equal to the first times the derivative of the second plus the second times the derivative of the first. And that is going to look like 1 over ti minus j plus the natural log of tk. That's your original r of t. We're going to dot that with u prime being 2ti minus 2tj, plus r prime of t. The derivative of r prime is negative 1 over t squared I plus 1 over tk, dot with the original u of t vector valued function t squared I minus 2tj plus k. You can simplify that to get the derivative with respect to t of r of t dot u of t is equal to 3 plus 1 over t. Now for the cross product, to find the derivative with respect to t of u of t cross product with u prime of t, we can find u prime and u double prime and use the property, which would be u of t cross u double prime of t plus u prime t plus cross with u prime t. We can set this up as a vector valued function in the form of a matrix where we have the original u is t squared minus 2t plus 1, and u prime being 2, 0, 0. That's u double prime, sorry. For the first cross product, u prime with u double prime. And then the second cross product, okay, we'll see that the second cross product is u prime cross with u prime, which is equal to the 0 vector. And when you simplify this by determining the value of the cross product, we find that that ends up being 2j plus 4tk.